Hi, I'm Soham and I'm going to talk about development of the telescope test structure for stability measurements of the LISA telescope, which will be done at University of Florida. The LISA telescope is needed to exchange light between the three spacecraft in the LISA constellation. The schematic looking inside the spacecraft shows two telescopes which receive light from the optical bench, magnify it, and exchange it with the far spacecraft. The telescope is a part of the test-mass science interferometer and is therefore subject to the 1 picometer per root Hz length noise requirement, a long-term length stability requirement of 1 micrometer over mission durations, and the sub-ppb backscatter light requirement. The telescopes are a NASA deliverable, and the telescope prototypes will be tested for their dimensional stability requirements and backscatter light requirement at University of Florida. If you want to know more about the work at UF, an overview talk of all telescope work is given by Dr. Pep Sanjuan. I will talk about the development of telescope test structure for length noise stability measurements. And Dr. Ada Uminska's talk will detail into the simulation framework developed to study the optical properties of the TTS plus telescope. The dimensional stability of the telescope will be measured by building an ultra-stable cavity around the telescope such that the telescope is a part of it. Figure 3 shows a conceptual arrangement of the telescope inside the TTS and the cavity is closed between the two mirrors. So, the TTS needs to be designed such that there is provision for internal alignment between the telescope and the TTS. It should be big enough to accommodate the roughly 84 cm long and 40 cm tall telescope and meet the stringent stability requirement, which means the TTS itself should display stability better than the LISA requirements. Hence, the TTS will be based on ULE, an ultra-stable glass substrate. The CTE of the structure should be similar to that of the telescope, as we will conduct our tests by creating a thermal environment similar to what is expected in flight for LISA. The details about the thermal environment development are in the overview talk by Dr. Pep Sanjuan. Figure 4 is a more realistic model with current designs of the TTS and the telescope. The TTS will have additional metering cavities which will act as a reference and won't be a part of the telescope cavity. While we don't think we will need them, they allow us to measure the stability of the TTS itself and subtract it from the full measurement to extract only the telescope stability. Before building something this big and expensive, we wanted to test smaller, scaled down versions of the TTS. Figure 7 shows the schematic of the basic principle for the measurement. Two 1064 nanometer lasers are locked to two cavities such that the light is always resonant in them using the Pound-River-Hall locking technique. The length noise measurement is a relative noise measurement against a stable reference cavity, which is 0-Dur spacer in our case, and has been previously measured to be more stable than the LISA requirements. Pickoffs from the two lasers are overlapped to generate a beat note signal which will drift as the cavity length changes. Hence, any length noise above the reference cavity length noise can be attributed to the test cavity. Both cavities are placed inside a vacuum tank and on an optical breadboard suspended via blade springs. This can be seen in figures 5 and 6 respectively. Additionally, we will have layers of thermal radiation shields between the tank and the experiment to reduce the coupling of temperature noise at lower frequencies. This thermal plus mechanical isolation is necessary to meet the requirement in LISA band, and this is a challenge to integrate the telescope in a similar level of isolation. Figure 7 shows the telescope with the TTS, but in our measurements so far, we don't have the telescope and we have tested the cavities for different TTS designs. Cavities built using optics bonded to ULE or 0-Dur, like the reference cavity I just showed, have shown exceptional stability and they work. However, they have no adaptability for any structural or optical design changes. So, we designed a cavity which is built out of 4 different ULE plates. These plates are joined together with a dowel nut and screw mechanism. A steel plate is screwed into the ULE end plate and provides a track for the mirror. A standard retaining ring plus spring washer is used to push the mirror against the ULE, so the cavity length is defined only by the ULE plates. Additionally, all relevant forces between the pieces that constitute the cavity are perpendicular to the cavity axis and hence do not affect the cavity length. From an alignment perspective of the telescope and the TTS, having adaptability in cavity mirror positions and their tilts is critical and details regarding these alignment tolerances are discussed in detail in Dr. Uminska's talk. The measured CTE for the structure is less than 0.1 ppm per Kelvin. Important to note here that this is only an upper limit, as at the time of the measurement we were limited by the resolution in our temperature readout system, which has since been updated, and we will soon have a more accurate estimate for the CTE. The TTS meets the picometer stability requirement by an order of magnitude in most of the LISA band, as we can see in figure 9. Below 1 mHz, temperature fluctuations cause length noise to ramp up and rise to the LISA requirement. Above 1 mHz, we are limited by the reference cavity length noise, which is shown in green, which itself is limited by the readout noise. These results give us confidence that mechanically connected ULE pieces can be used for telescope lens stability measurements at the picometer level, and this design in particular has exceptional stability which can be scaled up to the telescope size and will meet the LISA requirement. However, procuring these big pieces of ULE and then machining them requires time and leaves limited room for big design changes. So, to reduce the turnaround times in such cases, we replaced the ULE end plates by super-invar end plates in the structure. The attachment mechanism is the same dowel nut and screw mechanism used in the ULE version. The optics are again held with the simple spring washer with a retaining ring. We added cavities on the sides to monitor any bowing effect in the end plate, as that was one of the relevant sources of length noise that came up with such a design. The CTE of this cavity is roughly 0.25 ppm per Kelvin, which is lower than that of super-invar but higher than that of the ULE. We started looking into some FEM models to understand the reason for this high CTE, but couldn't do so conclusively. The lens stability of this cavity, shown in figure 11, is also roughly an order of magnitude below the LISA requirement for most of the LISA band. However, it ramps up much faster at lower frequencies owing to the higher CTE of the cavity. In the millihertz band, its stability is again limited by the reference cavity or the readout noise. Above 10 mHz, there is some additional noise, but it is still an order of magnitude better than the requirement. Here we look at both results together. Above a mHz, both cavities show stability roughly an order of magnitude better than the requirement. Around 1 mHz, the cavities have identical length noise and are limited by the readout. The relevant difference in performance for us is at lower frequencies, where the ULE performs better than the invar TTS owing to the lower CTE displayed. In figure 13, we see the temperature noise in our measurement setup, which is at 100 microkelvin per root hertz. This is one order of magnitude above the expected in-flight temperature noise for LISA. This indicates to us that with the current TTS designs, temperature noise should not limit our measurement given a better thermal environment. However, there might be other limiting noise sources which could scale with length and cause a problem. In conclusion, ULE TTS has been tested and it has shown the required stability with significant margin. So in this design, we have a solution that will work for the telescope as well. All we have to do is scale this up to the big size. We have also tested a hybrid invar ULE TTS model which gives us the required stability, has additional adaptability and faster turnaround times, but also has a higher CTE than the ULE TTS. So as of now, we still prefer the ULE version to scale up the full size for telescope testing. Procurement process should begin towards the end of this year, and testing for the TTS will begin next year. Thank you.